Unfortunately, we are being very efficient. So we're going to get to Dr. Waju. Dr. Waju is the Robert T. McCluskey Professor and Vice Chair for Research and Development in the Department of Biomedical Informatics and Data Science. He's also the Assistant Dean for Biomedical Informatics at the Yale School of Medicine, Yale University. Dr. Zhu's primary research interests include biomedical natural language processing and data mining, as well as their applications and secondary use of electronic health records data for clinical and translational research. His research is funded by multiple agencies, NIH, National Library of Medicine, National Cancer Institute, National Institute of General Medical Sciences, National Institute on Aging, and the American Heart Association. Methods and tools developed in his lab have been widely used to support diverse biomedical applications, and he's going to talk about some today. Thank you.
Thanks. Thank you, Paul. Good morning, everyone. Very happy to be here to share with you some of our work on developing biomedical large language model and AI agents for different biomedical applications with a focus on mining biomedical literature. So since the release of ChatGPT, I think we all agree that the world is actually changed a lot with all the different AI applications. We see a lot of promising applications of AI. Then one question is why this wave of AI is different from the previous AI technology, like machine learning, right? So I listed here is about, on the right side is called emerging phenomenon of large language model. We all know large language model is the key technology behind this wave of generative AI. And the research has found actually when you increase the size of the model, you're adding more data, making more parameter for the model, those large language models don't just perform well on a few tasks, it performs well on all different tasks. That's what this diagram is showing you. When the model size increase, it can handle all different tasks. Suddenly, we can see AI become much smarter than the previous technology, okay? And then quickly research found it's actually not sufficient just building the foundational large language model. To solve real world complex tasks, we need AI agents. So now you see a lot of reports on AI agents, which really refers to those systems can act automatically to make decisions, to take action, to solve complex problems by itself with very minimal human intervention, okay? And if you look at the landscape right now, still a lot of paper published on building large language model. You probably see new model released like ChatGPT-5 now already, but there's also a lot of work actually moving more towards agent-based system solution, trying to solve real-world problem. And the problem I'm going to talk about today is actually biomedical literature mining. I think everyone here probably use the PubMed, right? So right now you enter keywords. What do you get? A list of paper, maybe hundreds of pages. Can you really find the information you want quickly? Sometimes yes, sometimes no. I usually flip like 3 pages, then I'm done if I couldn't find it, right? So how AI can change this, okay? There's already several kind of attempts I try to summarize here. The first one is in January, OpenAI actually released this deep research function. You probably already start using it, right? So it's not just applied to biomedical domain, but for any specific domain, they can actually generate a landscape review for any question you ask for that specific domain or topic, and give you cited kind of summary to all those issues, aspects related to that research question. Quickly, Google come up this AI core scientist. I think some of you might heard about it. It's a big splash of water. They actually show how AI agents can actually go read the literature, generate hypothesis for you, design a protocol for you, even do some analysis in the drug discovery area. And then quickly, more recently, on the academia side, Stanford team with other team also produced this called a BioMini agent system. What it does, it can go through different data sets, databases, different tools, different software to do analysis, like a single cell data analysis, come up some results. So as you can, there's a lot of effort actually towards this agent-based solution for biomedical research, biomedical discovery. But one angle we're tagging on is actually, if you look at all those systems, the interface they provide is primarily a chatbot, right? How you can talk to the agent through the chat interface. But if you really think about AI, is really going to enable you to more interaction, how human and the AI can work together to quickly solve a problem. So that's what I'm presenting today, is how we can use the visual analytics to integrate AI and human to solve biomedical questions more quickly. And instead of you do a keyword, you get a list of papers. Here we create what's called a semantic map. So this is a collection of all the Nature Science papers published in the last 100 years, about 300,000 papers. And each paper we embedding it to the hundreds of dimensions using large language models. Then you do dimension reduction to a 2D dimension. Then similar paper will be grouped together, okay? Each dot is a paper here. And you can color those paper by the topic or by the time. Right now, I color it by the time. So the red dot is more recent paper. And the size of the paper, I based on the citation of the paper. So then you can really get quick overview of this entire landscape of a research topic you are interested, right? And then we can do a lot of more fancy, like a 2D, 3D, move to 3D space, and also do kind of a trend analysis. So I have a time sliding bar. You can see over the time how those research topics actually pop up. And if you look at on the right side, right now it's blank, but clearly you see the COVID cluster actually pop up at the end, become the big red dots on the right side, right? So those are the things give you more kind of overview of the entire landscape. And the other thing I mentioned is how can we improve the interaction between human and AI? So in this interface, this is a collection of all the GLP-related study for the weight loss drug. And as you can see, there's a lot of different clusters. So we actually provide a very interactive way for you to select the cluster, to search. Then once you have a cluster, we add it to a collection. Then you can, what do? You can just ask questions. Like we have this Copilot. You say, oh, this is a collection of 4 clinical trials. What are the phase? How many participate for each trial? You can just ask using your voice, and we will get the answer. Then you can interact with it to get more information out of those collection of papers. Hopefully, quickly help you to identify those research questions you have. And then another thing we did, I think it's interesting, is also, you see this is semantic space, okay? There's a lot of blank space. You may be wondering, what could it be in this blank space? Might be a research area you want to explore, right? So now we have an algorithm. If we click one of the points of this blank space, we will converting this kind of embedding space to a research hypothesis. Yeah. So hopefully, I don't know if it really makes sense in this, but it gives you some sense to think about this might be something new. And then I'll talk a little bit about technology behind the scene for this kind of AI application. This overview, we have data processing level, we have the AI agent level, visual analytics level. For example, we can load all 36 million of PubMed into one interface. That's actually a lot of engineering work. But what I try to emphasize is a couple of, one is about this biomedical foundation model. So in addition, you can use like ChatGPT, Llama, kind of embeddings from general domain, large language model, but you can also continue pre-train using biomedical data based on those open source models. That's what we did based on the Llama model. We continue pre-train using a lot of biomedical literature, clinical notes, guidelines, about 129 billion tokens. This will using 150 GPU training for a month. You hopefully get a better embeddings for the biomedical data. And then the second one is about kind of visualization technology. So I think some of you probably use the UMap and you do a clustering. You see a map like this with different research topic, but it doesn't really tell you who started this research area first, right? So then we have a new algorithm actually trying to encode the time to this layout. What you will see after we did that is something like this. We call it the iris view. So from there, what you can do is for each of the class along the timeline. So the radius actually goes through the timeline. The inner is the older paper, the outer is more recent paper. And you can see actually, okay, on this cluster, here is the first paper actually leads to this kind of research direction. And maybe a few other papers actually slightly twist to little bit different research direction, but kind of help you quickly identify how this journey of this research topic. And the last one, I just quickly mention like what is the algorithm behind this decoding of this empty space. So the idea is actually from this Google paper, they have this called embedding language model. What they did is, okay, you have two movies, Forrest Gump, Inception. How can you suggest a movie idea which combines the styles from both movies? That's what they did. They come up with this description of this potential new movie can combine both styles. So we took this idea, then we go to the literature. We find all the conclusion sentence, which is the main finding of each paper, right? Then we also say, here's the original text, here's the embedding space. And what we can do is do a fine tune is we assume we found this embedding space, we generate the text. Then we compare the generate text with the original text from the actual paper to define the loss function, to fine tune the model. And we turned out it's actually pretty good if you look at compare the decoded text from the embedding space to the original text. If you read carefully, it's actually quite similar. So that means we can more accurately decode from the semantic embedding space to this human readable text. So those are just a few kind of technique behind this. I think I'm running out of time, but just quickly, I hope you're convinced it's actually AI is changing how we do research, and agent AI powered by large language model, I think it will change the way how we do our research. Literature mining is just like one application. And to me, my personal interest is, I think, how to interface between human and AI. It will be very interesting and a big research topic. Thank you.